Thank you. I want to talk about an alternative to the idea of a world-based grid-like coordinate frame, and instead think about something like Hans-Peter Mallet wrote about in the 1990s of a graph of locations. And I particularly want to emphasize the idea of a hierarchy and how this applies to our representation of location and of layouts. So here's an example of a hierarchy of categories. Suppose you saw this, you might classify it as an antique blue jar. Well, that's one of, out of all possible objects, that's a large category. And if you had more expertise, you might describe it as a Delftware jar, and a real expert might describe it as a London blue Delft jar from the late 17th century. And the point is here that they're all the same stimulus, but there's a hierarchical classification according to expertise or training. And in the 1990s, I did an experiment looking at 3D shape that came to a similar conclusion. So this is a category of convex shapes, and concave shapes are the other half. And bas relief shapes are a subset of those. These are the shapes that are all the same ratio of depths, but different stretches along the z-axis. Just like the Parthenon is a squashed version of real shapes. And finally, in the center of this classification in this hierarchy is Euclidean shape, the full structure of the surface. And we could show psychophysically that the visual system used these different levels of hierarchy because it had different performance for each. I just want to say in passing that deep neural nets don't have this hierarchical structure, so they can learn about blue objects in a high-dimensional space. They can learn about spheres in the same dimensional space, but they don't have compositionality, so they can't put the two together. They can, of course, recognize blue spheres, but they can't do it from what they've learned about blue objects and spheres. They have to learn a new category. And what you really want is for blue spheres to be a subcategory of the category of spheres. But for that you would need an extra dimension, which deep neural nets don't have, so that not blue spheres are in one part, blue spheres are in the other part, but both project down to the spheres domain. So blue spheres and not blue spheres remain part of the coarse scale spheres category. So here's what I'm going to talk about. I've already talked about representation of an image, hierarchical representation of object shape, and in the remainder I want to talk about hierarchical representation of location, the paper we did in 5 years ago, and hierarchical representation of layouts, for example in a maze. And both of these using the same hierarchical framework that I've just introduced. So first of all, location. I want to thank the people who've contributed to this work, and I'm particularly going to talk about papers that Alex Murray, who's now in Russia, has done. This is a model he wrote about where this plane represents a set of egocentric representations, and a representation in his case was for n points there are n squared angles between those points. And if you start off by thinking about the mountains or distant points, then there's a large set of locations in which the angles between those points are essentially the same. So many different locations, the mountains, the angles between the mountains remain the same. As soon as you introduce near objects like these trees, you restrict the representation to a much smaller range of locations. So the angles that you're measuring may define the location much more precisely. And if you have even nearer objects, like this picnic table, and you include the angles between the picnic table and the mountains, the picnic table and the trees, etc., then you can define your location more precisely. So just as we saw before, it's a subset of the others. Location is being defined hierarchically. So instead of having coordinates on a grid like this, say latitude and longitude, we've got something more like a postal address. So the mountains are like the UK. Introduce the trees, it's more like London. Introduce the picnic table, and you get finer and finer descriptions of where you are. And this, I think, is more like what the brain is using. So this is an experiment that Alex did, and it's about layout or representation of layouts and of pointing within a maze that is not stable. It has wormholes in it. And so this is Ho Chi Minh City, which is a very confusing place to go to because it doesn't have a grid layout. But you might learn routes between two locations early on when you go there by following a route and familiar landmarks as you go, long before you could accurately point between those locations. So here's the virtual reality experiment where we tested this comparison between route following and pointing. So participants explore this maze. They have to go up to these boxes before they can find out what's in them. And then they're looking for red, green, blue, different coloured targets, which they must then find a route between and point between. And here's a map of someone doing the experiment, exploring, finding the different targets. And what you want to look at is the blue dotted line and the red dotted line. Because when the participant goes through them, they're like that, the maze changes, it's a wormhole, and as they go back through the blue dotted line, they go back into the stable maze. And they do a lot of looking at different targets, moving between different targets and pointing between them. And this shows the wormhole that you've just seen drawn out, and below it the topological graph of the layout of the maze. And the point is that with all the changes we made, all the wormholes we added, the topological graph remains the same. And this shows the 3 wormhole condition. So this is deeply confusing for participants. You can see the wormholes marked by the blue dotted lines and the red dotted line, and each of these wormholes drawn out on the right. 2 other wormhole conditions. And these are the results for the walking performance in the stable maze, in the 1 wormhole condition, and in the 3 wormhole condition. It really doesn't change very much compared, as you'll see in a moment, to the pointing performance. So by performance, I mean walking distance relative to the shortest possible route, and I've normalized it to the stable maze performance in the stable maze. So this is the results from the pointing experiment in the same environment, these are, I'm showing the angular offset for pointing from the green, and basically people are pretty good at this, other than the condition where the wormhole gets in the way, and the yellow and the green are separated by the wormhole. So here you can see the pointing from the green to the yellow, and most of the pointing is about 180 degrees in the wrong direction. And now you can do the reverse. You can say, well, when they're at the yellow, how do they point to the green? And again, they get about most of their pointing is in 180 degrees in the wrong direction. So they're trying to point from the yellow to the green, and they get it very badly wrong. Now you can say, what is their representation of where these objects are? So you can do a maximum likelihood exercise where you allow the 2D locations of the objects to move freely until you best explain the pointing that they gave. So this is for one participant. So in the most likely configurations, green is to the east of the yellow. That's what I show on the right. So this is the original, the true locations. And if you move that over, it's a much better explanation of their pointing to the black, the blue, the red, and the yellow. Okay, so that's what we did. Okay, so what's the explanation of that weird pointing? Well, it's as if they take the whole of the wormhole, a set of corridors, and squash it into one region of the stable maze. So they take these three, all this wormhole complication, and they say it must exist somewhere between where they go in at the blue dotted line and come out at the red dotted line. They must be in there. So if you take the, that's where the physical location of the green target is. But when you take into account the pointing that we've just talked about, their mental location of where the green object is somewhere in there, in that bit where they've squashed the wormhole. Okay, now we can compare the results for route following and for pointing that we've just talked about. We've seen the route following before. It doesn't vary very much with the different wormholes. Now we can look at the pointing performance, and that really does vary. So normalizing it to be the same in the stable maze environment, it gets much worse for one wormhole and again worse for three wormholes. And the definition of pointing is standard deviation of pointing errors normalized to the stable maze performance. Okay, so now we can think about this in terms of the same hierarchy that we've talked about before. So route following is a very broad category. There are many different layouts that are compatible with the same topological structure. But once we add length in, so this is the idea of a labeled graph that Castile and Warren talked about. So you can add extra information per edge in the graph. Then we're dealing with a much more restricted set of layouts. And you can keep going with that idea and add more information. So you take the edge between this yellow and blue point, and now instead of just having length, you have numbers of turns and the angles of each turns. You can build up a representation that's a much smaller region of this hierarchical set of layouts, and you can go all the way up to something that's behaviorally equivalent to Euclidean map. Okay, so this is what I've talked about: hierarchical representation of an image, of object shape, of location. That was the model Alex built, and the experiment that he did on layouts, and all referred back to this idea of a hierarchical representation. And the point of that is that it avoids any reliance on a 3D coordinate frame, which I think the brain finds very difficult to implement. Thanks very much.